Part 3. So how does this carbon cycle work? How do we distinguish stocks from fluxes? A stock is a measure of how much material there is. A flux is a measure of how much is going into or out of a stock. So let me use the analogy. I make $100 a month and I spend $100 a month. Both of those are fluxes, what goes into and out of the system. The stock would be, how much money do I have in my checking account? How much money do I have in my savings account? And so the flux would be, how much comes into my account, how much leaves the account. So I might have $1,000 in my savings account and $100 in and $100 out every month. Those are fluxes and stocks. Now you might say I'm not very rich because my income and expenses are only $100 a month. But what if I told you that my income was $100 and my expenses were $100, but I have $10 million in the bank? Now you might have a different impression. The point here is that we need to distinguish fluxes from stocks. We do that in the carbon cycle. So first let's ask something about fluxes. So what is the distribution, stocks, what is the distribution of biomass in marine and terrestrial systems? This box here represents the sum total of all mass on land and in the ocean. And what you see is that marine and terrestrial plants occupy about 450 gigatons of carbon. Archaea, 7, bacteria, 70. Protists, 4, fungi, 12, and animal systems, of which we are so fond, only 2. And if we take those 2 gigatons associated with animals, it turns out that most of it, half of it, is associated with arthropods. Humans are about 0.06. Annelids, fish, and mollusks, livestock, and cnidarians are actually more abundant in mass than are humans or wild mammals. Those are stocks. But when we talk about the carbon cycle, we're typically talking about fluxes. Your textbook and the Canvas graphic show this very daunting figure. I want to point out that a gigaton of carbon is equal to 10 to the 15th grams. While this graphic might be daunting, we can break it into some simple components. I've circled 2 colors, the red for fluxes and the black for stocks. What I want you to see is that most of the carbon on the surface of our planet is associated with stocks. Most of it sits in sedimentary rock and sediments, followed by the amount that's sitting in the deep ocean. If we begin to look at the fluxes, though, what we see is that the fluxes are about equal going in and out. So we get about 90 gigatons of respiration coming out of the ocean every year, and we have about 92 gigatons going in. On land, we have about 120 gigatons coming out and 119 going in. So the fluxes are very close to each other on land and in the ocean. Where humans come into play and we're altering things is that we're adding about 8 gigatons of fossil fuel every year. We're also adding about a half a gigaton to 1 gigaton, depending on how much forest we're taking down. Because we are adding it, the question might become, how much of this carbon which we're adding ends up in the atmospheric reservoir or ends up as part of the fluxes? What you can see here is that we get about 8 gigatons coming from human activities, and about 3 of those gigatons fall out as a net increase associated with photosynthesis. About 2 gigatons extra fall out because of marine photosynthesis. So 2 plus 3 is 5. So 5 of the 8 gigatons of carbon that we as humans emit every year fall out as photosynthesis. Thank you, plants, for subsidizing my activity. But the other 3 end up resulting in an increase in CO2 concentration. So that's a very quick way of looking at stocks and fluxes. We need to keep a time perspective here, though, because on an annual time basis, what happens in the marine and terrestrial systems is something we can influence. Those change over a period of 1 or 2 or 3 years. On a millennium scale, measured in thousands of years, we can change the ocean circulation. So it's not really possible for us to hide all the carbon that we're respiring through human activities in the ocean, because it doesn't work on an annual scale, it works on a millennial scale. Nor is it easy for us to hide that carbon in geological materials, because most of the carbon which is stored in rocks takes millions of years to be deposited. We can begin to calculate how much photosynthesis is taking place and how much the land and the ocean biota are responsible for CO2 changes by looking at the 2 processes. First, photosynthesis, that takes CO2 out of the air, and second, respiration, that adds it back. We can describe the productivity of a biome based on how much photosynthesis is taking place minus how much respiration is taking place. We call that net primary productivity, abbreviated as NPP. If we go to some locations on Earth, such as the rainforest in the Amazon Basin, we find that they can have large sinks for net primary productivity. On the other hand, drier ecosystems, such as shown here for the Joshua Tree Forest in California, are drought limited. Stomates close in response to drought, and net primary productivity is much lower. So that not all land surfaces have the same rate of primary productivity. Here's a map showing variation in terrestrial plant productivity. And the discussion we're going to have now, or you will have had with your neighbor, is where is productivity the highest, and is there a latitudinal pattern? In the ocean, it's important to recognize that most of the primary productivity takes place with single-celled organisms or single-celled organisms that come together to form chains, known as phytoplankton. One of the very common phytoplankton includes cyanobacteria, a plant that we've known, or a bacteria that we've known from previous lectures. Among the algae are some of the most beautiful and intricate and spatially symmetrical organisms known as diatoms. This diverse group is responsible for about 20% of the world's photosynthesis. They come in circular forms. Some species look like starbursts. Others look like a piece of rice or wheat checks. It turns out that there's also geographic variation in oceanic net primary productivity, with some regions having low productivity and other regions having very high productivity. That stands out in this image. Now the clicker question is, where do you think oceanic NPP is highest? Why do you think oceanic NPP is highest at the coast? Pick one word to explain your decision. Second clicker question, is NPP produced by prokaryotes, eukaryotes, or both? The answer is C, both.